So,
Okay, and
okay.
I'm clear and everything?
Yep, you are loud and clear. You sound good. We see your screen, so I will let you add it.
All right, thank you. All right, so I have my pointer. All right, well, thank you everybody for joining us today and, on this webinar. And I'll be talking about some work, that I did before joining Gamry. And the topic is really on electrochemically active biofilms. And, the purpose of today is really to just kind of touch on why we care about electrochemically active biofilms and, how do you use EQCM to study their growth on electrodes. And I don't have biofilm slides to go over. This isn't really a biofilm focused, looking at like biofilm formation, quorum sensing, and things of this nature. So I'll just start with why biofilms, why is Gamry even talking about biofilms? Well, I think that electron transfer in biofilms as a whole is a emerging field. I think everybody has known about it, but the methods to study electron transfer in biofilms, I think, has been recently, has really been taking off in the past couple of decades. And I think that everybody here either wants to know more about this electron transfer in biofilms, how it's occurring within biofilm, and what they can do with that information. And I think that this has a lot of implications, not just in maybe microbial fuel cells, if you are familiar, but just detection in cells as a whole. So, if you're looking at cells in the body, out in the environment on surfaces, hard surfaces, soft surfaces, porous surfaces, wetted surfaces, then you know that once that biofilm touches that surface, it irreversibly changes it. And it does so by ways that cells are really good at, putting down a conditioning film and all of that. If you are new to biofilm research and you would like more information about this, please contact me directly after the webinar, but otherwise I'm going to jump in. So the perspective for this webinar, and I've touched on it, is really I wanted to help biofilm researchers looking for a system, with a low barrier to entry into EQCM. I think you'll find that in what's available commercially, isn't really compatible with the needs of biofilm researchers. Normally, and this is in my experience, that we tend to have to piece together different parts from different vendors in order to make something work. And the idea of actually growing a biofilm in situ in an electrochemical system is one thing, and then adding on top of that another device like a quartz crystal microbalance, it gets really challenging. And so that's the perspective that I'm going for. And ultimately, by the time we're done with this webinar, you should have some kind of practical framework to run EQCM experiments for your biofilm research, with minimal time investment. I think if you come away from this webinar thinking that you know a little bit more about how you could attack this problem of running these measurements or making these measurements, that's a good thing. And that's because I would like you to be able to focus on your actual research questions that are probably more complex than just electrochemistry or just QCM, right? So, common tools to biofilm research. Typically, you have an autoclave for steam sterilization. You have some kind of biosafety cabinet, maybe a type 2, where you can ensure the what do you call it, the sterility of your sample and preparation. Or you might be doing anaerobic work in an environmental chamber, and a good example might be iron reducing bacteria and iron reducing biofilms. And you have some kind of basic PPE and protocols for disinfecting surfaces. And most likely as a biofilm researcher, you'll have access to microscopes, whether it's your own lab's instrument or it's a shared resource. And I put this list here because, you know, this is the kind of thing that most biofilm researchers have access to. And you know, when you go to grow your biofilms, you have to operate in a sterile environment, and you have to make sure that what's growing, you know, as a biofilm in your system is the culture or the strain that, you know, you expect. I mean, you don't want contamination essentially. So I put this list out there just to remind everybody that this is kind of what I have in mind when I'm thinking about biofilm research tools. Now, you want to integrate the QCM and a potentiostat, and you need some kind of EQCM cell and a sensor holder, and it has to integrate nicely with what you have as a biofilm research tools. And so that's what I'm going to cover today, and that's at the top here. Pictured here is the actual resonator device, the EQCM 10M. That's what I've used in the past, and this is what I used for all the research or the results that I'm going to show later. And, you know, I'm going to describe how this QCM works from a basic approach in terms of equivalent circuits. And then once we get over that, I will talk about the cell, what I've used in the past, what I know actually works with, you know, biofilm protocols and growing biofilms and reactors and all of that. And then I would like to touch on some of the applications. And this is probably the meat of the talk and where you want to, you know, ask maybe questions. And that is on how to actually grow the biofilm, the EABs in the QCM cell, as well as how to analyze them, or actually at least run some basic electrochemistry. And then we'll then finish up with looking at how we correlate the electrochemical results with the QCM data. So, oops. We'll start. What is QCM? Well, if you've never heard of QCM before this webinar, that's okay. This is your slide. QCM is just simply a device that it consists of a mass sensor and the electronics that control that mass sensor. And, you know, as a biofilm researcher, or, you know, somebody who's buying in equipment from a vendor, truthfully, you don't care about the electronics so much. And, you know, we only really care about how that mass sensor is working and what it's detecting and where it's detecting it. And maybe within the context of this webinar is what part of the biofilm it's sensing. And so we can discuss that towards the end. This mass sensor, the QCM, is sensitive or selective, excuse me, in that it only detects the mass that strongly attaches to the sensor. So you have a baseline response, and then let's say your biofilm forms, and then you should be able to only detect what that, basically the attachment of the cells that comprise of the biofilm. And the mass sensor is sensitive, resolving nanogram level mass changes. And that's what you would need if you wanted to study, let's say, cells attaching, you know, single cells attaching to a surface, or you wanted to resolve and detect that initial attachment of the biofilm onto the sensor surface. And so ultimately, if I had to say this in one phrase, you know, the reason why you're interested in a QCM is that it's a device that you can buy in, it's available commercially, and you can study film formation, biofilms, and other surface-related physicochemical phenomena. And that's important. And the EQCM part of it is also important because you can take a look at how a biofilm alters the microenvironment or the surface environment, and quantify that, and maybe use that information with different types of strains or mutants and get at your research questions. So overall, you know, if you think about sensing mechanisms and how you study biofilms, there's some information about microsensors and all of that. I pulled this figure from this book chapter here, but you can think of sensing mechanisms as falling into at least three categories, that two that we're interested in today, and then others. But the QCM is so-called the gravimetric method. You can search for it under that label, and you might be able to get more information. And of course, Gamry, we specialize in the know-how related to electrochemical sensing. And so typically, it's one or the other. You might be interested in just QCM, or you might be interested in the electrochemical aspect. And for us, when we think of electrochemistry, we're thinking about measurements that either are amperometric, measure current over time, potentiometric, measuring a voltage over time, and voltammetric, which is looking at voltammograms that change or vary with time, and as well as impedance, so looking at impedance over time. So ideally, when we talk about QCM separately, you're looking at a surface phenomenon, but when you couple it to an electrochemical instrument or setup, you get EQCM. And the whole purpose of combining these two sensing mechanisms is that you have access now to a surface that can be electrochemically modulated. And you take advantage of the fact that you can drive a current or measure a current or measure a voltage and drive current and measure a voltage, or run a CV and track what's going on with the surface. And that's where we're at. So the mass sensor. So what is the mass sensor? Well, it's a quartz crystal, and it has a particular cut. So if you look on the right here is a quartz crystal on XYZ axes, and the one that you will most likely use if you had to start EQCM measurements is the AT cut, which is shown right here. It has a resonance mode, which is, I believe it's called the thickness shear mode. That quartz is machined into a disc, and it is sandwiched between two electrodes. And you can see that here and here. The electrodes are used to basically cause oscillation in the quartz. And the quartz is used because of its piezoelectric behavior. And so what happens is you can induce resonance, and that is how we that's how we measure the mass. Okay. So if we take a look at the crystal, this one here, more closely, there are four important crystal parameters. The fourth one I won't cover. That's more related to QCMD and other impedance based measurements. But one is the area of overlap, the actual electrode surface area, and then the frequency of the crystal. So if you look on the left, you'll see that this is the quartz disc, and this is kind of what's called the can, and it makes contact to the electrodes. On one side of this mass sensor, you'll have a carbon tab, and that's, in this case, this is a carbon-coated quartz crystal, and this is your electrode surface. When you clamp this sensor into the cell, only this area approximately is going to be exposed to the solution for your electrochemistry. And on the flip side, and if you turn this over, you'll see the gold tab, right? And so this area right here defines the area of overlap, okay? And so the area of overlap is going to be, many times different than the area where your electrochemistry occurs. And for the most part, most people new to EQCM forget this mismatch. So, and we'll go over why this is important later, but essentially you can think that if you pass current in a larger surface area, but you only measure mass in a smaller area, if you try to correlate the two, like through Faraday's law, and then you correlate the mass change on the crystal, you'll notice that there's going to be a mismatch. So what happens when you apply a voltage across those two electrodes? Well, at rest, the crystal is just sitting there. It's not stimulated in any way. But when you apply an alternating potential to each electrode, you will cause the crystal to oscillate. And you'll cause that oscillation if the frequency of the alternating potential is equivalent to what's essentially called the fundamental frequency. And fundamental frequency is here, this F naught. And this is purely dictated by the crystal itself, the quartz. So here, the mu Q is going to be, and Q is for quartz, is going to be the shear modulus of the crystal, and the rho is going to be the density, and then the thickness. So the important fact here that you have to realize is that the fundamental frequency of this crystal, as it's excited, is purely a consequence of the quartz itself. And so for an AT cut quartz, this value for a given thickness is going to be nominally 5 megahertz. The results that I'll show later are, I think it's 10 megahertz. And so how does this happen? So you can think of QCM as an electromechanical system. I put this link here for Wikipedia. I think it's an interesting read, and it applies to a lot of different physical systems. But you can take the same crystal and look, again, this mass sensor, and you can look at a cross-sectional diagram, schematic of it, and you can assign what's essentially called the Butterworth-Van Dyke model. And here's a reference if you want to read up on how this is actually applied. But in general, the QCM as an electromechanical system, this is important because when you want to drive the quartz to its fundamental frequency and to get it to resonate, you have to interface it with electronics. And most commercial QCMs will actually extract the frequency information from a change in the electrical impedance or the response of the quartz crystal. So, this BVD model in general describes the electrical characteristics of the quartz crystal close to its mechanical resonance. And again, that mechanical resonance, that fundamental frequency, is determined by the dimensions and the cut of the crystal. But it can be, according to this, the impedance analogy, considered as an RLC circuit. And if you know about, hopefully you have a little bit of a background in this. If not, I can tell you that the R is related to damping and friction, and the tendency to impede motion. The mass, or the inductor, LQ, is related to the mass of the crystal that's actually moving in it. It's related more to the inertial, I guess, the force required to actually move and cause the deformation. And the capacitance, you can think of it kind of like a spring, I would say. And so you have the ability to store store energy, and that's often called compliance. You may have also heard of it in terms of elasticity. And so all of this RLC, the reason why it's important is because that LC, and I'll cover in just a bit, that resonating circuits are typically consist of an inductor and a capacitor in series or in parallel. And so the way that we tend to visualize the quartz resonating is that you tend to include the gold and the carbon into the circuit as an increase in the L, right? And with that, you can start to look at the L and the C. And what happens is you'll notice that we have an L and a C in series, and we have an L and a C in parallel. So what is, the consequence of having these two basically resonances? Well, if you actually went into into our software, EQCM Analyst, and you modeled an inductor in series with a capacitor, you'll get this kind of response so now this we're looking at is a Bode plot, and on the y-axis is your the modulus of the impedance. On the x-axis is the frequency, and on the y2, the secondary axis, is the phase angle. Just to backstep a little bit, essentially a Bode plot is allows you to look at impedance changes across the frequency. And so what happens is that, for an LC circuit, typically you start at a high frequency, and as the frequency is scanned lower and lower and lower, you'll hit a point where the impedance reaches a minimum, and this is your resonance. So in series, what you expect is a series LC circuit has a resonance where you have a minimum impedance. If you take an LC circuit and now make it in parallel, what you'll see is at the high frequency, you'll start here, and you'll start to see the impedance increase and increase until you hit a maximum in the impedance. And so the reason why I'm showing this is just that, the consequence of having both a series and parallel LC inductor and capacitors that you expect actually in the BVD model, right? You will expect to have a series resonant frequency and a parallel resonant frequency. And these are typically called FS and FP. And that's what you would expect from just a very casual understanding of the BVD model. And in practice, right, so here's some real data from this paper here of the quartz crystal, an oscillating quartz crystal in both air and in liquid. And so again, this is your Bode plot, but in this case it's split in two. So here's the modulus of the impedance, the phase angle, and frequency. And so you can see that this is a 5 megahertz crystal, and the impedance, right, is increasing to a maximum and then decreasing to a minimum and then leveling off. And so these poles, or the min max, this here is your series frequency shift, and this here is your parallel frequency shift. And so just by inspecting that, a simple model of an LC in series and a parallel, you expect a minimum and a maximum. And in your BVD model, you have a series LC and a parallel LC. And in practice, when you actually go to resonate this crystal, right, you'll see the consequence of this model. So in a sense, I'm telling you that the BVD model, it works, it makes sense. Now, what happens when mass is attached? And, let's say you don't really care too much about the BVD model. What you really care about is how the crystal is going to respond when mass attaches to one side of the electrode. So in this case, it attaches here. Here's this attached mass. It's supposed to represent biofilm. And what happens is, if that mass, if we treat it as an extension of the quartz, we can do what we did previously and say, oh, well, the mass is rigid and it's evenly distributed across the electrode, right? And it's much less than the actual mass of the sensor itself. We can treat it as an additional inductance, right? And if you remember, the inductance is related to mass here by the impedance analogy. So what happens is that before that film or that mass attaches on the surface, you have some baseline, right? So the series frequency will have some value here, right? And after the mass attaches, you'll get a new frequency shift, right? And that frequency shift, is basically going to be the new or the effective inductance of this oscillating system or the oscillating mass sensor. So since inductance shows up at the bottom of this ratio, then you'll know that you can expect that when mass attaches, a rigid mass attaches to the electrode, right, that you will see a decrease in the frequency shift. And so here, to show that in terms of a plot, and again, this is a Bode plot. When the film is actually loaded onto the electrode and you take your model data, and here's just, I modeled the BVD with a particular inductance and capacitance and resistance in order to get into a range that I could make the model in eChem Analyst. You can see that prior to the film introduction, we have a series resonant frequency here, just about above 1,000 hertz, a parallel at around 10,000 hertz. And so then when we introduce a positive finite film inductance, you'll see both shift, and they will shift to the left, and to the left means a lower frequency. And so the BVD model, right, is useful, and it's a useful representation to know and understand how this oscillating quartz crystal, the mass sensor, works. And what you basically we're leading at is that you know, a basic QCM and the resonator that we provide here at Gamry, it tracks FS and FP. And FS is this parameter that, if you know the information about your film, whether it's rigid or not, it will have a tendency that you will see that when a film falls onto the QCM or the mass sensor, there is a tendency for that frequency shift to decrease. And that's usually modeled as an additional RLC in series with the crystal, right? So one of the things to realize, I would say, is that if you look at the BVD model and you add your film properties, like add the film resistance and a film capacitance and a film inductance, right? You'll note that inductors in terms of circuits, they add in series, right? And that means that you have an increase in L, and now I'm reiterating from the previous slide, but if you have an increase in L, you expect a decrease in the series, the series frequency. If you have capacitance, your film has some capacitance, it has some elasticity to it, right? Capacitance adds in parallel, and that means that you see actually a net decrease in the total capacitance in this branch here. And what that means actually, and this is very interesting, right, is that if your film that's falling onto the surface is no longer rigid and has some elasticity, right, you can actually see positive frequency shifts. Why is that? And that's because if you look at this ratio for series frequency, that the capacitance, if the capacitance drops, you'll actually see a shift. So now that's interesting, because if you have a viscoelastic film, which is particularly what a biofilm is, you can have an increase in L and a decrease in C, which means that the series frequency shift that you're measuring, right, it can change. It can either be completely negative, or it can be, you can actually see positive shifts. And I won't, this is kind of getting into advanced topics about what kind of frequency shifts you'd see with a biofilm, but this is kind of one way to think about how a film loads onto the quartz crystal. I will say that FS and FP are typically insensitive to small changes in R. R again is kind of changes in viscosity, and so typically this is not observable with basic EQCM setups. Most of the time you're looking at this with some kind of ring down technique, or a system that monitors the full crystal impedance. In that case, that would be something like the QCMI system that we have. There's this second ratio that I look at, FP over FS. This is a consequence of the BVD model, and this tells you about, let me see. Here, this ratio tells you, basically allows you to detect changes in the film or capacitance on the motional branch of the quartz, right? So now, this might have been a little bit, if you don't have any background in circuits or electrical engineering, this might have been a little bit difficult to follow. What I'm basically saying is that a QCM, the takeaway message here and all of this analysis, that QCM tracks a frequency shift, right? And it does this by looking at the impedance characteristics of the crystal. And it's this impedance that the electronics is reading and running some kind of algorithm to pull out this information as accurately as possible, right? That's all under the hood, and this is important. It's important to note that certain impedance characteristics are linked back to the type of film that's being formed, right? But actually, when you go to, you run the QCM experiment, you get a frequency shift. What you're really mostly interested in is converting that frequency, that variation in FS or delta FS, delta F, right? You want to convert that into a usable, a parameter of interest. And in this case, most of the time, that's going to be a mass change. So the most basic fundamental equation to rely on this kind of conversion it's called the Salvary Equation. It was realized by a guy a while ago. His last name was Salvary, and what it's telling you is that the variation in frequency, the series frequency shift, what you measure with the QCM, right, this delta FS, is essentially going to be proportional to a bunch of constants and a mass change. So if you look at this list here, delta M is the mass change. Okay, so that's the mass of your film. The mu is a shear modulus of the quartz crystal. And again, this is cut dependent. So in this case, it's dependent on the AT cut of the crystals that you typically buy. This is a property, intrinsic property of the crystal, of quartz. Okay, rho here, it's the density of quartz. Again, it's a property of the crystal that you buy in. And F naught, the fundamental frequency. Again, this is a property of the crystal. Right? And N, if you don't know harmonics, it's okay. You can, we're talking about the fundamental, so N is 1, or essentially you're driving the crystal at its fundamental frequency. So in this case, a 5 megahertz crystal. So basically what this is saying is that you have delta Fs, which you read from your QCM, and the mass change, which is what you're interested in, and a bunch of constants. And what happens is this all gets reduced to what's called a calibration factor. And ultimately, right, this Salvary equation, this reduced form of the Salvary equation, is the practical form. Normally when you work with a QCM system, it measures this delta F. The crystal itself, the manufacturer, the vendor tells you that it has a calibration of factor such as 56.6, and then a bunch of units, and that's for a 5 megahertz AT cut quartz crystal. It doesn't matter if it's gold coated, carbon coated, whatever, or however it's functionalized, because that's inherent of the quartz, the crystal, and the area of overlap and the thickness of the crystal and all that. And so, now with the Salvary equation, there are a lot of assumptions built into making this correlation, and I'm not going to go into that here. That's going to be an advanced topic. But for most films, this is, I would say that this conversion from frequency shift to a mass change, it's not a true mass. And in fact, it's more appropriate to call it an apparent mass. And oftentimes you'll see it in literature as a Salvary mass. Okay. And so the punchline, for talking about, that the QCM measures a frequency shift, and then you can take that frequency shift and measure mass, right? The reason why we're interested in this is that if you take some experimental data, right, and you plot, and so I'll start here at the top left, that if you look at 3 systems that you'd expect to have 3 wildly or completely different films or film structures, right? You have a metal being plated onto a surface. You might have a polymer being electrodeposited onto a surface. and then you have the biofilm, which you're interested in. And in this case, this is like this is an SEM of a geobacter sulfur-reducing biofilm on quartz crystal. Right? A corresponds to A, B to B, and C to C. Well, here is plots of the delta F, which is the frequency shift on the y-axis, and time on the x-axis. So in this case, I won't worry about the details, but essentially you have copper coming down onto the surface. You see a decrease in the frequency shift, right? And I mentioned again that, I should back up. The black trace is your series resonant frequency, and the red trace is your parallel. So FS and FP. I mentioned that FP and FS, the ratio of the two tells you about essentially the elasticity of your film. So in the case of a metal film like copper, you expect it's a fairly rigid film and it's packed tightly. And in general, the Salvary equation applies for a copper film falling onto, depositing onto, let's say, a gold quartz sensor. You see that both the FP and FS track together. And at some point, you can strip it off immediately and you can get back to the original frequency. So in other words, you can measure or detect the process of deposition, and then you can actually reverse that and get back the original frequency shift. In the case of a polyaniline, I don't know if you're, I encourage you to look it up, but essentially, the initial deposition of polyaniline is rigid, but as you deposit more and more polyaniline, you'll start to see a divergence between the series frequency shift and the parallel, and this is related to the elasticity of the polymer. And in the case of biofilm, there is it's a complete divergence. And so, this is powerful in the sense that without even knowing much of the theory, just having a basic understanding of how QCM works, you can actually differentiate three types of films. Now, I'm going a bit slow. So QCM, EQCM, electrochemical quartz crystal microbalance, you can imagine, it's when you interface the resonator, the QCM, with the potentiostat. And the advantage here is that when you sync the two instruments, you have the ability to induce absorption, desorption, and changes in a film by electrochemical change or electrochemical methods. And that's exactly what I was showing here. Now, I will jump into biofilms. So, yes. And so from now, prior to this, we're talking about just QCM. Now we're looking at EQCM. And at this point, I wanted to touch on what system works for EQCM and biofilm growth. This is what I've used in the past, and I found that it was actually quite easy to integrate into biofilm protocols. But this list tells you about essentially things you need to consider when you choose an EQCM cell for biofilm growth. One, right, it has to be easy to sterilize. If it's not, you'll spend most of your time battling contamination. And that's a real challenge for students, especially people who are learning to use a system. You want the quartz crystal to be easily removable because chances are you want to send your biofilm for sampling, whether it's imaging or some kind of biochemical analysis. You want standard electrode geometry and electrode parts, and that's because you want very accurate and precise and clean electrochemical data. And obviously, if there's built-in gas purge, you can work with anaerobic biofilms and also replaceable parts. So the system that I found was the most compatible with that list is this Absorption Probe. And on the left here is, you'll notice this is a quartz, the sensor. The quartz is actually encapsulated in a plastic coating, and only the electrode is facing solution. On the back, which you can't really see, is going to be the area of overlap. And this sensor has two tabs here that slide into what's the wand, and that wand actually fits very nicely into a jacketed 200 mil Euro cell that we provide. And so the reason why it's useful is because actually you can convert this jacketed Euro cell or the RDE cell kit into basically a biofilm reactor. I won't spend too much time on this. I would just say that 2440 ports work nicely with the number 4, number 5 rubber stopper. And what that means is, you know, a rubber stopper, these butyl rubber stoppers are typically autoclavable, right? And most of the parts that come with the jacketed Eurocell kit are autoclavable. So in fact, you can assemble the complete cell, you know, minus the working electrode and the reference electrode, and you can send that to and get that autoclaved in your typical steam sterilization protocol. And that completely takes out all the effort with trying to clean complicated reactors. And then at the end, you know, you can just essentially poke a hypodermic needle into the system for flow. And so that's the system. I use basically the Absorption Probe as my QCM sensor, and then I coupled that to an electrochemical cell shown here. And now I'll jump into electrochemically active biofilm. So this is my standard slide for electrochemically active biofilm or bacteria. And you know, this is really, these are biofilm and bacteria or microbes in general that transfer electrons to and from a solid electrode and has the machinery to do so. If they don't have the machinery, the molecular machinery to do that, then you can consider that the biofilm can also generate a product that is electroactive. So a good example is maybe an algae or something like that that produces oxygen, and you can actually reduce that oxygen at an electrode. So in that sense, you know, it's quite general. You know, I tend to think about this kind of study of the electron transport in biofilms as biofilm electrochemistry. It's just simple and easy to understand. And you know, one of the things that you have to be aware of is that when you use electrochemical theory to study electron transfer of biofilms, you know, there has to be some level of causality. And that means that the electrode behavior, the current or the voltage that you're measuring, it represents the overall response of cells respiring in the biofilm, right? It's, you know, if it's not, then you're going to have a lot of difficulty, or it might be impossible to even get at the electron transfer in biofilm. So now I like to think of electron flow and the directionality of EABs. And that is that you can consider EABs that are either cathodic or anodic, and this is more for environmental biofilms, you know, thinking about where can you find microbes. You know, typically a cathodic EAB is found in an oxidized environment in the presence of oxygen. This is in oxygenated waters or in the presence of other, I guess you can imagine weird systems. But these guys, these EABs, cathodic EABs, tend to accept electrons from the electrode, and they tend to force the electrode potential, if you measure the OCP, towards more positive voltages. And these are typically metal oxidizing bacteria. Leptothrix discophora is a good one. You can look that up. It's a manganese oxidizing bacteria and biofilm, and they grow biofilms. Anodic EABs, they grow in a reduced environment, such as anodes and microbial fuel cells and the sediments, and they tend to donate electrons to the electrode and force the electrode potential more negative. And these are typically metal reducing bacteria. Schwannella is a good example in the field. In particular, I talk about one species, Geobacter sulfurreducens. These are biofilms on electrodes. They were found to grow on electrodes, and the first publication on this was back in 2003 by Daniel Bond. What Geobacter does, it's an anaerobe, and it will metabolize acetate and produce generally carbon dioxide protons and electrons, and ultimately it can use an electrode as the terminal electron acceptor. And when you grow this biofilm in EQCM system, and here's the image, you will see that most of the biofilm, and it's this pink hue here, is formed on the gold itself. If you've ever grown biofilm in lab, you'll know that they tend to grow everywhere. But these EABs and Geobacter specifically, it grows, I would say, cleanly. And this is actually a good sign that, when you're studying the EAB, there's some causality where the biofilm is actually growing only on the electrode and nowhere else. Right? So current is a proxy for biofilm respiration rate. Now, to activate this half reaction here, acetate to protons and electrons and basically carbon compounds, you have to polarize your electrode above a certain value, that threshold value. That is a measured value in the literature. It varies from microorganism to microorganism. In Geobacter, if you polarize the electrode above minus 0.4 volts versus silver chloride, a reference electrode, you will cause current to flow. And when the current flows, you'll start to get biofilm growth. And so, what happens is you polarize your electrode, let's say 0 volts versus silver chloride. You add cells in suspension to your cell. In this case, it's that Euro cell with the sensor. And what you'll see is that you'll see this type of response: current on the Y, time on the X. And what happens is you see current increase slowly over time. And what that is the cells that you added initially here, they are attaching to the electrode. They're forming an initial biofilm. And that initial biofilm is metabolizing acetate and producing electrons at a particular rate. And that rate is proportional to the actual respiration rate of the cells. And so you can imagine that if you plot the current in a log fashion and make a semi-log plot, you'll notice that there is some kind of lag phase and then leading into exponential growth. And so this is a good indicator that yes, the current that you measure from an EAB, especially such as Geobacter, is a proxy for, it's basically a growth curve. Now, what you can do during this, and this is just kind of basic biofilm electrochemistry, at any time during this growth phase, you can actually stop the voltage or the chronoamperometry script. If you're using one of our potentiostats, you can stop it, and you can run a simple CV between minus 800 and 200 millivolts. This should be millivolts versus the reference electrode, and you start negative, and you can sweep the voltage. And what you can do is, and this is a typical CV analysis in biofilm electrochemistry, is you can basically measure the onset or the activation of that half reaction, metabolizing acetate to protons and electrons and CO2. And so what you'll see is from the start is no current or baseline current, and then all of a sudden an increase and a ramp, and then a decrease, right? And so what this is essentially a catalytic wave. If you're familiar with electrochemistry, this is an EC prime mechanism where there is an electrochemical reaction that you're monitoring, and it is being fed electrons at a particular rate by a coupled chemical reaction. And in this case, that chemical reaction is the metabolic activity of the cell. If you were to actually take away acetate, you would no longer see this catalytic wave. And you'll notice that this wave here, right here, the sigmoid, oftentimes will have some kind of redox behavior superimposed on the wave. And that is actually a very nice indicator of possibly the mechanisms at play that allow the electron to go from the inside of the cell to the electrode. So that kind of molecular machinery. I won't go into those details. We're sort of out of time. But now you can look at, a lot of times people have trouble in this field because you're measuring a current and you think that there's biofilm. You're not sure because really this is an indirect measurement. The current is increasing. It has a semi-log behavior. It looks like an exponential growth curve, and it seems to be that I'm getting more current and seeing these voltammograms over time. But is there biofilm? I have to do some secondary analysis to get at this question. But with an EQCM, you can track it at the same time, right? So here is frequency shift versus time, and that's this upper left panel. So you've got the series frequency shift on the y-axis, time on the x, and I'm not going to cover this reduced Q for time, save time, but at time 0, as you see the current is increasing, you will also see the frequency decreasing, right? And so this goes back again to our understanding of our mass sensor in the QCM, and that when you see a drop in the frequency shift, right, from the baseline, you have mass attaching onto the surface. And one of the most interesting things that you can do is actually plot the current on the x-axis and the frequency shift on the y-axis. And you'll note that there is, what looks like a line, a linear response. And this is saying that, and this is interesting, right? Because now you have cells growing and dividing in the biofilm, and you're saying that, wow, the current that I'm measuring, which I think is a proxy for the biofilm growth, it's telling me that for a given frequency shift, I get an equivalent, or sorry, for a given amount of current, I get an equivalent amount of frequency shift. And if frequency shift can be, turned into a mass, it's telling me that for every packet of mass or for every cell that gets added to the biofilm, that results in a net increase in current. And so you might say, well, that looks like a line, but it's not really linear. It looks like there's some parts where it's like going it flattens out and then it decreases. So if you look at, here, this comes from a paper that we published a while back. If you look at the closer, initial attachment, now this is the same current versus time, and then frequency shift on the secondary axis. You see that for these red arrows, you'll see is where we added the cells in suspension. Right? So, well, actually, they were added closer to 0, but as soon as those cells touch the surface, the electrode, you see an immediate jump in current. And at the exact same time, this is the EQCM setup that we've been talking about. At the exact same time, you see a drop in the frequency shift. And that's, and then when you transform that again to current and frequency shift, you'll see this perfectly, even in this zone of rapid increase in current or rapid jump or drop in frequency shift, you will see a straight line, right? So even here we're at microamp scale up to 40 microamps. Even at that very beginning, when you see her in the nanoamp region, when you've got more, I would say, cells actually dropping onto the surface and then starting to propagate, you'll see that you tend to see this linear response. Right? And one of the things you can do is you can compare that to a conductive polymer like polyaniline, and you can track, this is the image or the plot from the previous slide. You can also plot frequency shift with the total amount of electrons passed in terms of moles, right? And so if I converted this, just integrated this current, if I integrated this current, you see that it's not linear. But for something like polyaniline, where you basically require, it's Faraday's law, if you require you require a stoichiometric amount of electrons to be deposited to add to the film, right? So you would expect actually that if you plotted frequency shift with the amount of charge passed, you'll get a straight line. This is true for depositing copper and other films, but in the case of biofilms and the cells that are actually actively respiring, you won't get a linear response with the charge passed. You tend to expect to see a linear response with current, and this tells you that, and this makes sense because the original assumption is that current is a proxy for respiration. Well, this is proof because for every amount of biofilm that is formed on the surface of the electrode, you will get an increase in current. Right? And this is kind of the power of EQCM for studying EABs. Other things that you can look at is that you can run CV and you can monitor the frequency shift during a CV. And one of the coolest things about this, and this really hasn't been touched in the field, not that I'm aware of yet, is that you can see transient frequency shifts without allowing the biofilm to grow, but just by changing the oxidation state. And this is saying something like, so here's the frequency shift when there is no current, it's in a reduced state. When you sweep the voltage, from negative to positive, you see a decrease in the frequency shift. And so it's telling you that there is actually a structural change in the biofilm. You can detect this structural change. It's related to the oxidation state of the biofilm. And this can tell you things about solvent and counterion moving through the biofilm, basically mass transport in the biofilm. So you would not know that this is occurring unless you had the QCM, right? And most people in the literature have these CVs, and when you couple it to frequency information, you start to see that, hey, we should look at information that's not just about the flux of electrons in the biofilm, but also a flux of protons, and not just protons, but counterions, and maybe even the flux of nutrients through the biofilm, right? And how solvent can actually move in and out of the film. So in conclusion, I'll leave you with that, this is kind of a limited amount of time, but, EQCM really can provide you, if you're studying EABs, and with a lot of information. And, this is just basic QCM, and basic QCM compared to a lot of the other equipment that you can buy in is relatively inexpensive. And if you do it right and you have a setup like the Absorption Probe and what I've described to you, you can actually study, very accurate, or I would say clean electrochemistry along with the biofilm formation, and kind of get at how biofilm accumulates on the surface. Additional resources, I would say a lot of what I covered is in chapter 5 of this book that we put out a few years back. This year we're having a course on this. It's a 3 to 4 day course. It's in Washington State, in Pullman, Washington, at Washington State University. It's scheduled for late July, but I don't know. It kind of depends on the trajectory of current events, but we may or may not postpone it. If you have questions about these two resources, just let me know. And I'm done.
Okay, thank you, Jerome. So we are going to, we have some questions that we can ask now, and I think we might even have, be able to have people raise their hands and ask questions, and we'll unmute them so that then they can ask you too. But I'm going to start with an easy one, since here we just finished up the biofilm itself. Is EQCM an appropriate tool to monitor biofilm activity on surfaces outside of the laboratory and within industrial water systems?
So the answer is, I have been asked this at conferences in the past, because, this is good. It's a nice tool to play with in the lab. But in industrial water systems, I think you can buy quartz crystals, the sensors, with a functionalized surface that is, more representative of the surfaces that the biofilm will attach in service. So what I'm saying is that, for example, if you're trying to study biofilm attachment in pipes, I don't know what kind of pipes, plastic pipes or metal pipes, and with different alloys or makeups and whatnot, you can probably find a surface, a crystal, or modify a quartz crystal so that you can study the attachment using QCM. Now, adding the electrochemistry component of that, that's a little bit challenging, because if it's not, if you're in a plastic pipe, there's not much there for electrochemistry. But if it's a metal pipe, then, galvanized pipe, then that's something that you can study. So you can find you can look at information such as like microbially influenced corrosion. I know that that might be something that people are interested in.
Okay. Okay, thank you. Next, we have a question from owner. Let me unmute him or her. Okay, yes, please go ahead. Okay, maybe we're having some difficulty there. Let me mute and get back to that person. Let me ask another question that was posed here in chat. Do you need to start with a new crystal or electrode for each experiment you do, or can you clean them like RDEs or something else?
So I will address this question just for biofilms. If you have a good cleaning protocol that you know and can be sure that you can remove the conditioning film that typically goes down when biofilms actually form on a surface, then you can reuse them. Depending on how harsh that treatment is, you might actually start to eat at and slowly degrade the gold in our case. You know, you can strip away that gold, or you can eat away at the underlayer and basically cause that electrode to delaminate from the quartz. When that electrode delaminates from the sensor, you will not be able to, or you'll just get really bad frequency data, and that sensor is useless. If you're not sure that your cleaning procedure is removing all of the impact of a biofilm, I would not reuse crystals. In my experience, I have never used a crystal twice. But you know, at the same time, these crystals can get expensive, but I think with careful planning, you can manage that cost. So practically, okay, I would not, but
okay, that makes sense.
Negotiable.
Okay, so we have another question here. Is there any relation between uniformly deposited mass and linear response of QCM sensor?
I mean, that's one of the assumptions, is that you have a uniformly deposited mass or a layer over the crystal, and that's kind of allows you to make that conversion from frequency shift to mass. You know, in biofilms, and I didn't touch on this, but you know, biofilms don't attach as a uniform layer. They hardly ever do. There's some kind of nucleation or aggregation, and that's just a cell manages to make it to the surface and attaches to one part of the electrode, and then from there, you know, if the conditions are right, it grows, so it spreads out from specific clusters. And so if you're familiar with biofilm theory, then you'll know that you know, a single cell on the surface will propagate itself along the surface, and you'll get biofilm aggregates. And once these aggregates get large enough, they start to, you know, coalesce. I don't know if that's the right word, coalesce, but into that larger biofilm that you see, like for example, what I showed with the biofilm. So that entire process, it's hard to say, assume that biofilm through all growth phases is going to be a uniform film. So that is, I think, one of the challenges with pulling out quantitative data from EQCM. What I've shown is really qualitative understanding, and then hopefully, you know, you could take the qualitative understanding and try to dig deeper. But
okay, okay, we have a couple questions. And I'm going to try to generalize them because they're close to one another. But basically, several people have asked: is there a way to assess the strength of adhesion of a biofilm through EQCM, or how can you ensure that your mass is strongly attached to an electrode?
So from a practical standpoint, and I didn't show this, but you can try to convince yourself. You can flow. For example, if you have a strain and I know certain biofilm groups, research groups have strains where they can knock out some of the adhesins for biofilm growth. So you can create a mutant that you expect no biofilm growth whatsoever. So in other words, you have your QCM sensor, you have your non-biofilm forming strain, you introduce the cells in the presence of the QCM, and you won't see a frequency shift. You just won't. And then you can compare that to the strain where you get strong biofilm growth and you'll see a frequency shift. That's a practical way of looking at it. Other ways, otherwise, yeah, it's not, there has to be a strong coupling between what is being attached on the crystal, right? In order for it to actually dampen the crystal response. So in order to see that series frequency shift, I mean, there has to be mass that is rigidly attached, and that rigid really means that you can treat it as kind of a part of the crystal. If you've got some kind of tether and you've got this long dangly chain of biopolymer and it's far away, it sticks out like a hair from the electrode, right? You will only be able to detect probably the anchor part of that whole complex. You will not be able to pick up what's like far away. And this is what I've seen with thick biofilm. You can put single cells down onto the QCM and you can fairly easily measure them. But as the layers grow and grow and grow, it's really difficult and it's actually impossible to measure cells that are a certain thickness away from the crystal surface. So it's complex. Yeah.
Okay. I just want to remind everybody, I'm getting a lot of questions here, and they're all varied. And I want to remind you that we are saving the chat after this. So if we don't get to your question here, please also drop your email address to one of the co-hosts, and we'll follow up separately to try to answer the questions. But we're going to try to get through a few more. But if we don't get to it, please make sure that we have your email address and we will follow up. So I'm going to let's see, we have Elijah has raised his hand. And let's go ahead and unmute him to let him ask his question. Elijah?
Yeah. Okay. Thank you, Jeremy, for the presentation. I really appreciate that. I have just 3 related questions. I've been working with a group in which we use microemulsions to produce nanomaterials. And recently we acquired an EQCM. We were supposed to start, but because of the health challenges, research has been stopped. Now, the questions I want to ask are, now, if you want to make a deposition on a crystal and then you study the mass by the EQCM, is it advisable to do like a blank study initially before doing the deposition from your from your solution in which you actually wanted to deposit nanomaterial? And then the second one is, how do you prevent external vibration from affecting the signals or the frequency that you obtain from the crystal? And the last one is, after deposition, how do you easily wash your crystal so that you don't remove the deposit that you have on it?
Sure.
Those are my questions. Thank you.
Yes. So on the second one, well, I'll start with the third one. The washing, that depends on what's there. So if you're microemulsion, I don't know how a film is forming from there, but you have to verify. So you can try to deposit your film, and then while the sensor is running, you can try to wash it off, rinse it off, and then bring it back to its initial state. And if you can do that, that's a good way to practically estimate whether you can clean your crystal. Otherwise, you can also do some kind of post-analysis to see what residues are there. There's a good chance that even though the frequency shift is the same as the initial, there might still be some residue on there. So it's worth looking at just analyzing the crystal before and after. In terms of and I forget the first question. For
That's the blank. I was the first question is the blank. I mean,
So-
before you start depositing.
right, and so normally how this system works, and I didn't have time to show it, is you normally have a blank solution and that has, does not include what you suspect is going to form your film. And so I don't know what that is in your emulsion, but you generally collect a certain amount of frequency shift data, and that you call as your baseline, and you establish that as your baseline. All of the plots that I showed, a good example, let me see if I can pull it up. Here is, there is going to be a baseline value, and I just cut that off from this data, but I had at least 30 minutes of stable background data where I did not have any cells, so I didn't have my agent that would form the film, right? And that's considered your inline blank. And then you will tend to spike in whatever, or flow in whatever is going to form your film. And then at that point, you'll know when you introduced the agent or the film forming agent, and then you will see the frequency response. Well, you expect to see a frequency response. And then your second question was?
The second question was to prevent external vibration from
Okay.
being recorded in the
So
signal.
the particular cut of the quartz is an AT cut. It's a thickness shear resonance, and that is, it's a weird. It doesn't actually displace, I would say, vertically, like maybe a tuning fork would or something like this. So actually, the QCM, as you would buy it, is fairly insensitive to vibrations. If you have to isolate it, you can just put it on a granite slab and that tends to arrest most of the vibration you get from buildings. Or you can actually, if you really need that to completely remove that effect, you can work on some kind of floating tables. And these are just tables that have a pneumatic system in the legs, and they're essentially floating. You can think of like air hockey, if you're familiar, but essentially that, so.
Okay, thank you.
Okay, let's see. Let's apologies if I mispronounce the name. Sajad ask a question. She has he or she has their hand raised. So please go ahead.
Hello, everyone. You say that the acetate is the source of the carbon oxide. Why only acetate? I'm asking if any other source can be used.
So any other carbon source can be used for different strains or different microbes. In this case, it is just simply known that Geobacter will use acetate as an electron donor. It can produce electrons by also turning over hydrogen and maybe other secondary metabolites, but in the literature, most of the systems feed the Geobacter with acetate. If you're using other strains, for example, if you're familiar with the literature, Schwannella onadensis, you can use lactate, pyruvate, or any basically carbon source that the microbe will be able to metabolize, basically.
Okay, thank you.
Yeah, it just depends on the metabolism and what's known about the microbe. So.
Okay, thank you. Jerome, since we're on this slide or somewhere close to here, there was a question. Can you repeat what happens in EQCM when a biofilm becomes less rigid or less elastic? Or less rigid or elastic?
So, so less rigid and less elastic. I would say you might be referring to this slide where, you can see, so a frequency shift during a CV experiment. And so this CV experiment is, I think it's 10 millivolts per second, a scan rate, and it works out to be 5 minutes. So in the course of 5 minutes, you can basically modulate the frequency shift, or essentially the apparent mass or the Salvary mass of your biofilm. And that's interesting. So, you know, this type of frequency shift response is basically looking at, and this is what I think, you know, my interpretation of the data is a change in the elasticity of the biofilm. And this is actually supported by some in situ NMR measurements that we made. If you're interested in these measurements, contact me afterwards. I'll give you all of the references. But essentially, when biofilm is in a reduced state, an inactive state, it tends to collapse on itself. And you know, collapse is a very general word saying that basically the void spaces in the biofilm kind of collapse, and so it becomes more rigid, right? And once you actually drive current flow, which means go from the left side of this graph to the right side of this graph, right? You oxidize the parts of the biofilm and you force current to flow. Because electrons are flowing, there has to be a counter-ion flux, and this can be done and achieved. This mass transport can be achieved in multiple ways. One of the ways it can happen is you can actually have solvent come in and out, or come into the film. And what happens, you know, in our prior NMR studies is you would see diffusion rates, or the diffusion coefficient, actually increase with, you know, this polarization or oxidizing of the film, right? And that's in line with a drop in the frequency shift, right? Because if your film goes from maybe collapsed, more rigid, to kind of more open and more porous, you tend to see more of a elastic change, or a change in the structure or the formation of the film. This is not known quantitatively. I don't know if anybody has really looked at this beyond just looking at the frequency shift data. This is very similar to how polyaniline and other intrinsically conducting polymers behave when you basically oxidize and reduce them, and you dope them and undope them, right? So this phenomenon is actually known and quantified in other polymer systems. But when you're looking at biofilms and other biopolymers, it's actually, it's comparable, but I don't know if the exact mechanism is known. So.
Okay. We've had several questions now asking if you can couple EQCM to other techniques. One of them could be SECM, or perhaps if you could couple it with a fluorescence technique. Do you know of any examples?
I don't know. Actually, yes. Not. So the EQCM, you know, coupling the electrochemistry, then the QCM, and then some other sensor. If that sensor is an electrochemical sensor, like a pH microsensor or an amperometric sensor, you know, you have to be careful of the crosstalk and ground loops and other issues between the potentiostat that you're using for the EQCM and that sensor. If it's an optical sensor, or if it's a microscope, you can actually get ITO coated crystals that are transparent. And so you can actually couple maybe fluorescence measurements in addition to the EQCM. Obviously, you can't use the absorption probe, and you'd have to go into some kind of specialized optical flow cell, but it is doable. And then at that point, you know, you can look at fluorescent changes as a function of oxidation state, as well as look at, you know, what that mass change correlates to. There is that OWLS measurement that, you know, I don't know if I should talk about this, Chris, but but basically optical methods are a good way to couple, are good to couple to EQCM. It's just a matter of, you know, spending the money to do it, I would say.
Right. Okay. let me see here and looking through some of these others. And again, if we don't get to your question today, it is getting kind of late. You know, we've been going for almost an hour and a half now. If we don't get to your question, we do have all of these saved in chat, and we will follow up, you know, within the next day or so to help answer some more of these questions. So with that, let me see if there's one more relatively straightforward one we can get. I'll ask this final one here. Can we use this method to evaluate the ionic liquid adsorption onto the electrode surface during electrolysis? It seems specific, but how about it?
Yeah, that depends on the viscosity of your ionic liquid. I think you would first have to establish that you could get the quartz crystal to resonate in your ionic liquid. For these ionic liquids, I would recommend that you not use the Absorption Probe and actually use the standard cell that comes with the resonator or other QCM, with the resonator. In my experience, for example, glycerol. If you ever work with glycerol or syrup or anything of that nature, you'll know that it actually completely arrests the resonance. So in other words, the R, you know, that damping effect of the solution is so high that it actually quenches the resonance, and the resonator cannot output, the electronics cannot output enough voltage or cannot drive that crystal. So that'll be your first concern. Otherwise, you know, with that kind of system, I would recommend actually going to maybe a QCMI system where you're looking at not only the frequency shift, but looking at bandwidth and assessing essentially the elasticity, the viscoelasticity of the film that your ionic liquid forms on the sensor.
Okay.
Yeah.
Jerome, sorry to interrupt. There was one small update to this question just now, and it's being specified that it's only a small amount of ionic liquid in water, so that the viscosity isn't high, it's actually quite low.
Oh, okay. Yeah, and that, so that, you know, now that depends on how the two phases partition out and whether they partition out on the surface of the electrode. So I think that has a lot to do with maybe hydrophobic and hydrophilic interactions. And you might choose a particular type of quartz crystal where you know that the ionic liquid will tend to adhere to. Otherwise, I'm not sure even if you mixed ionic liquid and water in an aqueous environment, whether it would actually stick to the crystal. So.
Okay. All right. So, I mean, from that though, we can get it's still it's a very complicated system to be doing it. So, okay, I'll tell you, I think we're pretty good there. I think we'll stop there. I want to thank everybody again for attending this webinar, those that managed to stick around to the end. We will have a recording of this that we will be posting, and we'll email you the link. It'll take us a little time to process it and get it ready and get it put up at the appropriate site. But we will follow with an email so that you can watch it again or pass it on to your colleagues. And then be on the lookout for more of these webinars. You know, there are more planned, and we will be looking forward to giving them to you. So anyway, thank you everybody for coming. Be safe, be healthy, and we'll see you again soon.
Thank you.
Thank you.
Thank you very much.